Hello everyone, in this video we will cover the section 12.5. In this section we will see the equations of lines and planes in three-dimensional coordinate system. First we will remember a line in the xy plane, actually in two-dimensional coordinate system. If you remember, it is determined when we know a point on the line and its slope, or if you know the direction of the line. So the equation of the line can be written using the point slope form. For example, so first we sketch the two-dimensional coordinate system, x-axis, y-axis, and if you know a point whose components can be given as x0, y0, and if you know the slope, if you remember, it is stated as y minus y0 is equal to m times x minus x0, where we take a representation, a general point on the line whose components are given as x and y. For any point stated as x and xy, the equation of a line in two-dimensional coordinate system can be given by using the point slope form. Or if you know, if you don't know the slope, but if you know its direction, which is known by defining a direction vector for the line. Let's say v has the components v1, v2. If you know the direction vector of the line and a point x0, y0, if you don't know its slopes, also we can state the equation of the line. First, we find another vector on the same line such that we will see two vectors on the same direction, in the same direction. So the second vector is obtained by combining the points x0, y0. We know a point on the line, and we take a general point on the line to find its equation. So the initial point is x0, y0. The terminal point is the general point of the line xy. And you see two vectors, v and this one, are in the same direction, which means they are parallel since they are in the same direction, but the lengths can be different. Actually, we can say the vector written here is actually a multiple of the vector t, which is given by t times v, okay, since they are in the same direction. So from here we can write t times v is equal to the vector from the point, let's say p0 to p, which is the terminal point of the vector t times v. So it is the components of this vector can be found by applying the difference for the points p and p0, can be written as x minus x0, y minus y0. And we know v has the components v1, v2, and the components are equal to each other respectively when we have vector equality. Therefore we have t times v1 is equal to x minus x0, and t times v2 is equal to y minus y0. By finding t for each equation here, so we obtain a common number t as x minus x0 over v1, y minus y0 is over v2. Okay, so if you write this one as x minus x0 times v2 over v1 is equal to y minus y0, so you say this is the actually this is the point slope form of the line. Instead of m we have v2 over v1. Okay, v2 over v1. Similarly, in three-dimensional coordinate system, we will follow the similar way. We will follow the similar way. So we consider a line such that we know a point P0 whose components are x0, y0, z0, and we take a general point x, y, and z. You see. And every point has a position vector in three-dimensional or two-dimensional coordinate system. The red vector is denoted by r0, is the position vector of the point P0, and the blue one is the vector of which is the position vector of the point P. Okay, and we know the direction of the line L, V, the vector V, and the position vector of this one is located here, the vector V. We know a point, we know its direction vector, okay, and we want to find a general form for the equation of a line in three-dimensional coordinate system. So similarly, we can obtain another vector A, which is the black vector on the line, by combining the points P0 and P. So A is actually has the representation P0, P. The vector A has the representation P0, P, and the vector V has the components V1, V2, V3, and we are in the same direction for the vectors A and V. Therefore we say A is a multiple of the vector V, since we have the same direction for these vectors. Okay, and from here actually we have a triangle law for the vector addition, namely the vector R, which is the blue vector, is actually the vector addition of the vectors R0 and A. The vector R is equal to R0 plus A. Okay, and we know A by using the components of the vector V. Therefore we obtain a vector equation. The vector R is equal to R0 plus the vector A, which is a multiple of the vector V, which is the direction vector of the line. So this is called a vector equation of the line in three-dimensional coordinate system. Each value of the parameter t here gives the position vector of a point on L, which means by changing the value of the parameter t, you will obtain vectors which are the position vectors of the points on the line. Therefore, actually, you find all the points on the line by considering the terminal points of the position vectors. Okay, so just writing a number for t, we obtain the points of the line in three-dimensional coordinate system by using the vector equation representation. Okay, this is the first form for stating an equation of a line in three-dimensional coordinate system, and it is called vector equation. So if the vector v that gives the direction of the line is written in component form as ABC, if you know the components of the vector v, then we have t times v, which is actually the vector A, instead of v1, v2, v3, we use ABC for the components. And we know A is a multiple of the vector v, t times v. Therefore, we write t times v is equal to ta, tb, tc. We can also write the position vector of a general point on the line as x, y, and z, namely the point P, we know, and its position vector is stated as x, y, z, and we know a point on the line in three-dimensional coordinate system x0, y0, z0. So using the vector equation and writing their components in this equality, we obtain r is equal to x, y, z, r0 is x0, y0, z0, and we have the components of the second vector. Therefore, using the vector addition algebraically, we obtain the right hand side in this form. So two vectors are equal if corresponding components are equal. Therefore, we have the three scalar equations: x0 plus t times a is equal to x, y0 plus t times b is equal to y, and z is equal to z0 plus c times t, where t is any real number. These equations are called parametric equations of the line L through the point P0 and parallel to the vector V. If we know the direction vector of the line and a point, we can find its parametric equations by using the formula as written here. This is the second form for the equation of the line in three-dimensional coordinate system. By using the vector equation, we obtain its parametric equations. And parametric equations for a line through the point x0, y0, z0 and parallel to the direction vector are given here. So let's find an example for this. Find the vector equation and parametric equations for the line that passes through the point 5, 1, 3 and is parallel to the vector I plus 4j minus 2 times k. Or we can write it has the components 1, 4, minus 2. So using the formula, r is equal to r0 plus t times v, which is a formula for the vector equation of a line in three-dimensional coordinate system. Our aim is to find r. We know r0, which is the position vector of the given point in the example. Therefore, we write 5, 1, 3 for the components of the vector r0, you see. And we know the direction vector because we know the line is parallel to the vector written here. Therefore, we consider it is a direction vector. So the vector equation can be found easily by writing the given quantities into the formula r0 plus t times v. So we obtain a vector equation, and from here we can see easily the parametric equations. The first component is x, the second component is y, and the third component is z. Okay, easily. So find two other points on the line except the given point. So how can we find another points on the line? Easily writing any values for the parameter t in the parametric equations. So we obtain two another points. For example, easily if you write 1 for t, we get the first component is 6, the second is 5, the third one is 1. So a point on the line is 6, 5 and 1. And similarly, by writing another value, for example -1, or you can write yourselves 2, 3 and so on, you can get a lot of points on the line. So in general, if a vector v is used to describe the direction of a line, if you know the direction vector of a line, this is a line in three-dimensional coordinate system, and on this line we have a vector, you know its components a, b, c, Then the numbers are called direction numbers. They are called the direction numbers of the line L in three-dimensional coordinate system. Since any vector parallel to V could also be used, we see that any three numbers proportional to the direction numbers could also be used as a set of direction numbers for L. By taking a multiple of this vector, so also you can find parametric or vector equation of a line. Any multiple of the vector V can be used for determining the parametric equations or the vector equation of a line. It is not important. You can use any multiples of the vector V. Another way of describing a line is to eliminate the parameter t from the parametric equations. You know, in the parametric equations we have x is equal to x0 plus a times t and so on. So from here we find t for each equation in the parametric equations. From the first one we obtain x minus x0 over a. From the second one, y minus y0 over b is equal to t, and z minus z0 over c is equal to t. We have the same parameter for each equation here. Therefore, by writing namely equation the results here, we obtain another form for an equation of a line in three-dimensional coordinate system, and these equations are called symmetric equations of the line. Okay, notice that the numbers a, b, and c. So we have three forms. Before this, we have three forms for stating the equation of a line in three-dimensional coordinate system. The first one is the vector equation. Okay, vector equation. The second is the parametric equations. Parametric equations. The third is symmetric equations. This one, okay? Symmetric equations of L. So the numbers which are the components of the direction vector appear in the denominators of the symmetric equations. So components of vector parallel to L can be 0, so we can still eliminate t. For instance, if the first component is equal to 0 for the direction vector of a line, so we could write the equations of L as if you want to use symmetric equations. So since the first component is 0, so just for the first variable we write x is equal to x0, and if the others are not equal to 0, so we still use the basic form for symmetric equations. Okay, if for example the second component, namely the direction vector, has the components a, 0, c, so we write x minus x0 over a is equal to z minus z0 over c, and we write y is equal to y0. Okay, if two of them is equal to 0, or if the direction vector is given by a, 0, 0, and so we write x minus x0 over a is equal to the parameter t, such that y is equal to y0 and z is equal to z0. Okay, so let's do another example. Find parametric equations and symmetric equations of the line that passes through the points A and B. At what point does this line intersect the xy plane? So we know 2 points on the line. We don't know its direction vector explicitly, but by using the given points we can find the components of the direction vector. They are the points on the line A and B, for example. You know, by combining the points A and B, we get a vector in the same direction of the line, which means we can easily find the direction vector of the line AB, which is the representation of the vector V. So the components of the vector V can be found by writing B minus A, namely 3 minus 2, minus 1 minus 4, 1 minus 3. So we have for the components 1 minus 5, 4. Direction numbers 1 minus 5, 4. If we know 2 points easily by taking the difference of them, we get the components of the direction vector of the line. And by taking one of the given points easily by using the parametric equations formula, you know 2 is corresponding to x0 in the formula, so we write 2 x0 plus, actually x is equal to, you know, x0 plus a times t times a, or a times t. So x0 is equal to 2, which is the first component of the point, and the first component of the direction vector is 1, 2 plus t. Similarly, y is equal to 4 minus 5t, and z is equal to minus 3 plus 4t. And symmetric equations from here: x minus 2 over 1, or using directly formula, y minus 4 over minus 5, z plus 3 over 4. So how can we find the intersection point of the line in the example and the xy plane? Actually, we want to find the intersection point of the line, for example this one, x-axis, y-axis, z-axis, and we have an intersection point for the line and the xy plane. Okay, so how can we find the components of this point, which is the intersection of the line and the xy plane? So the line intersects the xy plane when, you know, when we are in the xy plane, every point has the form, if you remember, x, y, 0. Okay, the third component is always 0 for every point in the xy plane. Therefore, we write 0 for z. Using the symmetric equations, the last term becomes 3 over 4, and from here we can find easily the values of x and y written here. So the line intersects the xy plane at the point 11 over 4, 1 over 4, and 0. Okay. So in general, we know from equation 1 that the vector equation of a line through a vector r0 in the direction of a vector v is r0 plus t times v. If the line also passes through the terminal point of the vector r1, then we can take the direction vector, and so its vector equation becomes in this form. The line segment from r0 to r1 is given by the parameter interval by using this representation. The line segment from r0 to r1 is given by the vector equation written here. Namely, if you want to find a representation or an equation for the line segment on a line in three-dimensional coordinate system, this is a line in three-dimensional coordinate system. You know already a point r0 is the position vector, okay, p0 of the point p0, and if you want to find an equation from p0 to p1, let's say x1, y1, z1, okay, and its position vector is r1. So we can find a vector on the line by using the terminal points of the positions vectors r0 and r1. By taking the difference of these points, we get a line, a vector, which is actually, if you sketch here again, p0, p1, and this is the origin, for example, and the position vector of the point p0 can be stated in this form, r0, and this is the position vector of the point r1, and we want to find an equation for the line segment from p0 to p1 without using the equation of the line L in three-dimensional coordinate system. You see, if we say this is the vector x, so r0 plus x is equal to r1. From here, x is equal to r1 minus r0, r1 minus r0. So from the general formula, a general equation for the line segment is equal to r is equal to the given point p0, and namely we write its position vector since we use the vector equation, plus t times the direction vector, which is the vector x for the line segment from p0 to p1, namely r1 minus r0. Therefore, from here, by distributing the parameter t into the parentheses, we obtain 1 minus t r0 plus t times r1. So from the first coefficient, t should be between 0 and 1. So this is the general formula for the line segment from the point p0 to p1. Okay. So now we see an important example. Show that the lines L1 and L2 with parametric equations L1 and L2 are given by the parametric equations. So show that the lines L1 and L2 are skew lines, namely they don't intersect. We don't have any intersection point for the lines, and they are not parallel, and therefore do not lie in the same plane. Actually, they lie in the parallel planes. We will see later. Namely, we don't have any intersection points for the lines like this. This is a line, and they have no intersection point in three-dimensional coordinate system, and the directions are different. You see, they are not parallel, so we say they are skew lines, like the box. For example, this is the base of the box. So we sketch a line for the top of the in the top of the box. This is a line, and we have another line like this on the base of the box of the rectangular prism, or on the base of the cube. So you see they are not parallel because the directions are different, and we don't have any intersection point for them because they lie on the parallel planes, such that the positions are different for the planes, okay, in three-dimensional coordinate system. Therefore they are called skew lines, since we don't have any intersection point and they have different directions. So how can we show they are skew lines? By using their parametric equations. So the lines are not parallel because, first let's see, they are not parallel. The corresponding direction vectors are not parallel. In order to say that the lines are parallel, so we have to have the direction vectors of them are parallel. So the direction vector of the first one given, which the components are the coefficients of the parameter t for each equation. Therefore we write 1, 3, minus 1. And L2 has the direction vector 2, 1, and 4. And you see we don't have any multiple for them. Namely, one of them is not a multiple of the other, you see. One is, if we multiply the first component by 2, we get the first component, but if we multiply the second component by 2, we get 6, but here we have 1. Therefore the first one is not a multiple of the second one, therefore they are not parallel, their components are not proportional. If L1 and L2 had a point of intersection, which is the second condition to say that they are skew lines, we proved the first condition. So we show they do not have an intersection point. So if we have any intersection point for the given lines, we have to have a common solution for the parametric equations, namely x are equal to the same number, y's are equal to the same number, z's are equal to the same number, which means 1 plus t is equal to 2s, minus 2 plus 3 times t is equal to 3 plus s, and so on. So, but if we solve the first two equations, we get t is equal to 11 over 5, s is equal to 8 over 5. These values don't satisfy the third equation. To get a common solution, all of them should be satisfied. Therefore, there are no values of t and c that satisfy the three equations written here, which means they do not intersect. So L1 and L2 are skew lines like this. Okay. A single vector parallel to a plane is not enough to convey the direction of the plane. Namely, we cannot use a single vector parallel to a plane to determine the equation of a plane, but a vector perpendicular to the plane does completely specify its direction. Therefore, a plane in space is determined by a point. If we know a point in a plane here, we know a point in three-dimensional coordinate system in this plane, and a vector little n that is orthogonal to the plane. So this orthogonal vector n is called a normal vector. Namely, if you know a point P0 has the components x0, y0, z0 in this plane, and if you know a vector which is orthogonal to the plane stated as little n or bigger n, so we can find an equation of this plane. Okay, so how can we find an equation? So we use a general representation for any point in the plane, let's say x, y, z, and we know already a point at the beginning on the plane, and we know its normal vector. So using these two quantities, we will find equations for a plane. So combining the points on the plane, which are P0, and let's say this is the point P, like this. Okay, we obtain a vector on the plane. We obtain a vector in the plane. Okay, let's say the vector V has the components x minus x0, y minus y0, and z minus z0. First, we will use the position vectors of these points to get a vector equation of the plane. You see, as I said, P0 is given all at the beginning, and its position vector is stated as R0. And we use a general representation for any point on the plane given by P, and its position vector is given R. And from here we obtain a blue vector on the plane. It lies on the plane, and we know its normal vector and a point. So you see x plus r is equal to r0. X plus if we start from the origin, so we write r0 plus x is equal to r. R0 plus x is equal to r by using the triangle law. So x becomes r minus r0, namely the vector v, actually the vector v. Okay, so you know n is orthogonal to the plane, which means it is also orthogonal to every vector on the plane. Therefore, the inner product of the vectors x or v and the normal vector is equal to 0, since they are orthogonal. So we write n inner product v is equal to 0, or instead of v or x you can write r minus r0. So this is called a vector equation of the plane. So to obtain a scalar equation for the plane, we write the components of the normal vector and components of the vector on the plane x minus x0, y minus y0, and z minus z0. Using the vector equation, easily we can find the components of the normal vector are a, b, and c. Inner product, the components of the vector on the plane x minus x0, y minus y0, and z minus z0 is equal to 0. So using the definition of the inner product, scalar product, you see a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. So this is called the scalar equation of the plane through the point P0 with normal vector n. For example, find an equation of the plane through the point 2, 4, -1 with normal vector 2, 3, 4. Find the intercepts and sketch the plane. Putting the components of the normal vector and the components of the point in the scalar equation formula for the plane. So we see that an equation of the plane, namely for A, B, C, we write 2, 3, 4, and x0, y0, z0 are equal to 2, 4, -1 respectively. Writing them in the formula, we get the equation of the plane written here, or by arranging this equation we can write 2x plus 3y plus 4z is equal to 12. Okay, so from here we see when we have an equation in three-dimensional coordinate system involving the variables x, y, and z, and we don't have its squares or square roots or any power except 1 for x, y, and z, and it is in the linear form, so we understand that it is an equation of a plane. Okay, and you should see the difference between the equations of a line and plane in three-dimensional coordinate system. So to find the x-intercept from here easily we write 0 for the other components y and z to find x-intercept, so it becomes 6. Similarly, by writing zeros for x and z to find y-intercept, so we get 4, and similarly z is equal to 3. They are the intercept points of the plane, which means the general form of the plane will be like this for its graph. So by collecting terms in the scalar equation, by collecting the constants from here, we can write, namely we write it is actually a times x minus a times x0 plus b times y minus b times y0 plus c times z minus c times z0 is equal to 0. And from here we have ax plus by plus cz is equal to, writing the numbers to the right hand side, so we have ax0 plus by0, they are numbers because we know already at the beginning cz0. Okay, so this one is called d. Okay, so we obtain ax plus by plus cz is equal to d here, or if you can say the negative one, so it is called a linear equation of the plane, linear equation of the plane. So find an equation of the plane that passes through the point P, Q, and R. So we know 3 points on the plane. So we want to find its equation using one of the forms of the equation of a plane in three-dimensional coordinate system. So if you know 3 points on the plane P, Q, and R. Okay, so by using them we obtain 2 vectors on the plane. If we combine the points P and Q like this, and P and R, so we obtain 2 vectors on the plane. And you know, if we take the cross product of them, we obtain a vector which is perpendicular to these vectors, which means actually we obtain its normal vector, we obtain the normal vector of the plane, because a vector that is perpendicular to them should be in the direction of the normal vector of the plane. Okay, because this is perpendicular to the plane, which means this is perpendicular to the vectors on the plane. Okay, by finding the vectors obtained by the points, as I said here, P and Q and P and R, so we obtain the components of them, and their cross product is orthogonal to the plane that can be taken as a normal vector. You know how to find the cross product of two vectors from the preceding section. So from here we obtain the components of the normal vector. So we know a point on the plane, and we know its normal vector using the linear equation written here. You see the coefficients of the variables x, y, and z are the components of the normal vector. Therefore we write 12x, 20y, and 14k is equal to 14z is equal to d, and we know a point on the plane. So writing the components of the point for x, y, and z, we get d actually. Let's write one is x, so we write 12 plus y is equal to 3, so we have 16 from here, plus 14 times z, we have 28 is equal to d, and 28, 60, 12, 72, 72, 80, 100 is equal to d. So writing 100 here and dividing by 2 each term, we get this one. Okay, so find the point at which the line with parametric equations intersects the plane given here. Let's solve this equation in the next video. Thank you very much.